Inductors and capacitors have a lot of things in common. Capacitors store energy in an electric field between the plates due to the charge buildup. Inductors store energy in the magnetic field in the coil due to a current. And they affect circuits in similar ways. So one of the things we did with capacitors was look at a time constant for the charging and discharging of that capacitor. And we can do something similar with inductors because it affects how fast the current builds up in the circuit and how fast it degrades. If we go around this circuit and do the loop rule, we get a differential equation. Your book works through the details, but I'll give you the solution here. When we solve this for I, we get the current as a function of time is the maximum current times 1 minus e to the minus t over tau, where tau is the time constant of this circuit. Now the time constant is a little different for an inductor. For an inductor, tau is L over R. Let's take a look at current versus time. And we could also look at the potential across the inductor as a function of time. If we're looking at the current, we saw in the last video, the instant we close that switch, we get no current because the back EMF, or the self-induced inductance, pushes back, causes a current in the backward direction, and at that instant we close the switch, there's no current. But the battery keeps pushing and that self-induced EMF starts to degrade because there's not an abrupt change like there was when you first closed the switch. And so this gradually builds up and approaches its maximum value. Now let's take a look at our circuit. If we're getting zero current when we close the switch, we've got a battery with a potential difference pushing current in one direction. And we've got an inductor on the other side that creates its own potential difference and pushes back. And if there's zero current flowing at that instant, the potential difference must be the same as the battery. They must be pushing with the same potential difference as the battery. And then over time, that drops off. And at infinity, it's gone to zero. It no longer pushes back at all, and our current is just E over R. What we just looked at was very similar to charging a capacitor. Now let's take a look at the similar situation to discharging the capacitor. We want to be able to remove the battery, but allow current to continue to flow. So this type of a switch is one way to do that. As you slide this switch from A to B, you never lose an electrical connection. And when it gets to B, you've removed the battery from the circuit, but allowed a path for the current to flow the whole time. So let's take a closer look at this. When the switch is at position A, the circuit looks something like this. And when the switch is turned to B, we've effectively removed the battery from the circuit. So let's take a look at what happens when we remove the battery from the circuit. We can do our loop rule again, and what we end up with this time is that the current in the circuit as a function of time is some maximum value times e to the minus t over tau. So when the battery is removed, the current doesn't just drop to zero instantaneously. That solenoid, that inductor, that coil of wire, had a big magnetic flux through it. And that flux starts to go to zero very quickly. And so it pushes hard to try to create its own magnetic flux to get back to its point of maximum flux. And it pushes the current through. So we were getting a current in the clockwise direction in this circuit. And when we removed the battery, that started to die down to zero, but the self-inductance, the induced EMF, caused the inductor to act like a little battery and try to push current in this direction to keep it going. Of course, it can't do it forever. So if we plot this, it starts out at its maximum value and exponentially goes to zero as time goes to infinity. Let's take a look at the energy stored in that inductor. We want to be able to quantify that. If we do our loop rule, now if we multiply this equation through both sides by I, let's see what we have here. That's the power supplied by the battery. I squared R is the power dissipated in the resistor. So this last term must be power delivered to the inductor. So if U is the energy stored in the inductor, the power is du dt. And when we solve this, we get U is 1/2 Li squared, energy stored in an inductor. That's very similar to what we got for a capacitor. The capacitor stores energy in the electric field between the plates. The inductor stores energy in the magnetic field in the coil. Let's take a look at this special case where we have just an inductor and a capacitor in a circuit and nothing else. Assuming our capacitor is charged, let's close that switch at t equals 0 and see what happens. I'm going to plot the charge as a function of time after we close that switch. The charge on the capacitor, that is. So at t equals 0, our circuit looks like this. The capacitor is fully charged. We've just closed that switch, but current doesn't start flowing immediately because of the inductance in the coil. So we have 0 current flowing and the maximum charge on our capacitor. Sometime later, the charge on the capacitor has gone to 0. We have our maximum current flowing, And at that time, of course, 0 charge on the capacitor. The current flowing will charge the capacitor up again, but with the plates oppositely charged. So I can plot this condition right there. The charge is maximum, but the charges on the plates are reversed. At some time later, I'm back to Q equals 0, and I've got my maximum current flowing, but in the opposite direction. And then I'm back to where I started. And I get a curve that looks something like this. And when you try to solve for the charge in this circuit on the capacitor as a function of time, you get this differential equation. And this may look kind of familiar. Remember in our mechanics class, we used F equals ma when we had something like a mass on a spring oscillating back and forth. And we said the force from a spring is minus kx. It's proportional to the displacement. And the acceleration is the second derivative of the position with respect to time. And so what did we end up with here? We ended up with an equation that says we need to take two derivatives of our function. X is a function of time, right? The position with that mass on a spring was a function of time. Two derivatives of our function, and we get negative a constant times our function again. And what did we use to solve that? A sine function or a cosine function worked to solve for that. That was a simple harmonic oscillator. Well, this circuit is a simple harmonic oscillator. Our mass on a spring, what was happening to the energy in our system? It went from kinetic energy of the mass to potential energy in the spring, to kinetic energy of the mass, to potential energy of the spring, and it oscillated back and forth that way. And as long as there was no friction in the system, it would oscillate back and forth like that forever. And what's happening here? The energy is stored in the electric field of the capacitor, then it's in the magnetic field of the inductor, then the electric field of the capacitor, and it goes back and forth like that. And as long as there's not a resistance in this wire at all, no resistor in this circuit, it'll oscillate back and forth like that forever. It's a simple harmonic oscillator. So there's our solution, just like it was when we did simple harmonic oscillators in mechanics. And what is this? That phase angle, that's just there to set the initial condition. Because I could have chosen a cosine function, I could have chosen a sine function, but I just need to shift. If I choose cosine and you choose sine, we both have to be able to start at the same place and get the same result. The phase angle is there to set the initial condition. And we have a term for this, 1 over LC, just like we did in mechanics. What did we call K over M? We said that was the angular frequency squared. Omega was the square root of K over M. So over here we do something similar. We say omega is the square root of 1 over LC. We call that the angular frequency of oscillation. And that's for an LC circuit. I think an example problem would help solidify some of these ideas. So we've got a capacitor and an inductor, an LC circuit. The capacitor is charged to 5 microcoulombs, and we're going to close the switch at t equals 0. First thing we want to know, what's the angular frequency for this circuit? Then we're going to find the maximum current in the inductor, and then the charge on the capacitor at t equals 40 milliseconds. L is 50 millihenries, C is 30 microfarads, I got 816 radians per second for omega, the angular frequency of oscillation. Now let's find the maximum current in the inductor. This is just like finding the maximum speed of a mass moving back and forth on a spring if you knew how much the spring was compressed. It's an energy conservation problem. All the energy initially is in the capacitor. So the total energy of the system is a combination of what's stored in the capacitor and the energy stored in the inductor. But at the very beginning, at t equals 0, there's no energy in the inductor. It's all in the capacitor. And I got 0.417 joules when I plugged in 5 microcoulombs for the charge on the capacitor and a capacitance of 30 microfarads. So we found the angular frequency, and now we're working on finding the maximum current. And we're using energy to do that. So now we know the total energy in the system, 0.417 joules. And at some point, all the energy is going to be in the inductor. And there's not going to be any charge on the capacitor. And that's when the current is at its maximum value. So we can set this up and solve for I maximum. And I got 4.08 amps when I plugged in the numbers. Now it says, what's the charge on the capacitor at t equals 40 milliseconds? So we can go back and use the equation we just got for that simple harmonic oscillator, that LC circuit. We said the charge as a function of time was equal to Q maximum times the cosine of omega t plus phi. Well, we need to figure out what that phase angle is to fix our initial conditions, and then we can use this equation. We know at t equals 0, the charge is its maximum value. When t equals 0, I just plugged in t equals 0 into my equation. I know this has to equal Q maximum because the capacitor is fully charged at t equals 0. That means that cosine phi has to be 1, or my phase angle has to be 0. So let me rewrite this equation. Q maximum, cosine of omega. Omega was 816 radians per second. And we're looking for a time of 40 times 10 to the minus 3 seconds. Remember to set your calculator to radians. And I get 1.7 millicoulombs.